Hello, everyone. This is the first lecture in the Introduction to Linear Algebra course. We will start, as you can see, with linear systems. So I'm going to explain what is meant by a linear equation, then what is meant by a linear system, and how can we use matrices in order to represent these systems, and later, how to solve them. So let us start. First of all, before talking about a linear equation, the first question that we should ask ourselves is, what is an equation? What is meant by an equation? If I'm given an expression, how would I know whether this is an equation or not? Very simply, it is a two-sided expression. What do I mean by two-sided expression? I mean there should be, for example, some terms here equals another terms here. So this is a two-sided expression. For example, you might have 3x plus 4y, let's say, equals to 7. That's an equation. Or maybe you might have 2x squared minus 5xy or yx, whatever, is equal to 3x, for example. That's another equation. So whenever you have a two-sided expression, we call it an equation. Now, when do we call an equation linear equation? When do we call it linear? As you can see in each equation, we have terms. So this guy here is a term. That is another term. This is also another term. Each term consists of this number, which is called the coefficient, this number next to the letter, and the letter. So this is called the coefficient, right? And the letter multiplied by this number is our variable. Okay? So coefficient, variable, and so on. Now, when do we call an equation a linear equation? We call an equation linear if and only if, in each term, if we have a variable, if there is a variable like here, like x, like the y, it has to have an exponent 1. So for example, this is 3x to the power of 1. That's an exponent 1. Plus 4y, this is y also to the power of 1, equals 7. Here we don't have any variable, doesn't matter. So as long as we do not have any variable that has an exponent higher than 1, we call it linear equation. So this is a linear equation. However, this is not a linear equation. Why? Well, two reasons, right? So first of all, we have x to the power of 2. That's an exponent which is greater than 1. Moreover, even if I remove the 2, let's say I remove the 2, this is still not a linear equation. Why? Because we have x times y. We have a product of two variables in the same term, so which also doesn't work for a linear equation. A linear equation does not have such terms. So in short, an equation is called linear if, in case we have variables, they must have an exponent 1. Beautiful. Now, our task here, of course, in linear systems, is that whenever you have an equation, you must, we'll try to solve this equation. In other words, to find the value or the values, if they exist, I mean, of these x and y, let's say. So my task is to find the values of the variables. By the way, it doesn't have to be, it's not necessarily x and y, right? You might have n variables. It's not necessary that we only have 2 variables. I don't know. Okay? Perfect. So that's our goal. Now, so what is meant now by a linear system? Very simple. If I have more than one equation, so let's say, let me just clean it up here. So for example, you might have something like 3x plus 2y minus 5z, let's say, is equal to 1. And maybe y minus 3z, for example, equals to 5. So this is what? This is a linear system. So a linear system has more than one equation. Next, let me show you how to generally represent a system with m equations and n unknowns. So let's say we have the unknowns x1, x2, x3, xn, These are the unknowns that I am asked to find, right? And how would I represent a general system, a general linear system? I'm going to use special indices when I represent the coefficients, and I'd like you to really focus on these indices because it's very important. They're going to play a major role when we define a matrix. Let me show you. So the first equation, I'm going to write it as A11. This is the first coefficient. Well, Y11, don't worry. You know what? Let me change the color. So A11 times x1. What is x1? Of course, it's our first variable, right? Plus A12, that's the second coefficient, times x2 plus A13. Of course, you might notice, you might have noticed that the first number in these indices is not changing here, and the second number is increasing by 1, right? I'm talking about the a's, the coefficients, x3. Why is that? I will explain. Plus, etc. Plus a1n xn, that's the nth unknown or variable, equals to some constant b1. So that is the first equation. That is equation number 1, right? What about equation number 2? So now I'm going to start with 2. So a21 x1 again, plus a22 x2, plus a23 x3, plus etc., plus a2n xn equals to b2. That's the second equation. So I said that we're going to have m equations, right? All right, etc. So the last equation will be a m1 x1 plus a m2 x2 plus a m3 x3 plus etc. plus a mn xn equals to bm. Now this is a general linear system. But wait a minute, what is going on here? What are these? Before answering this question, let's think of these as follows. So these are going to be raws, right? So each equation is a raw. And these guys here, I'm going to think of them as columns, right? So the first column is the column which contains all the terms which have x1. You see? The second column is that which contains all terms that have x2 and so on, right? The last column will have what? Will have all the terms, or will contain all the terms which contain the xn's. So how many rows do we have here? We have m rows. How many columns? Why? Because we have m equations, right? How many columns do we have here? We have n columns. Why? This is the first column corresponding to x1, then x2, then x3, then etc., then xn. So of course we're going to have n columns, right? So n columns. So n columns and m rows, right? Now, the first index in each of these coefficients always corresponds to the number of the raw. And the second index will always represent the number of the column. So let's look at it again. That is the first raw and the first column, right? So RC, this is how I remember, I memorized it, right, when I first learned it. So RC, raw column, 1, 1, this means that I'm talking about the term in the first raw and the first column. Let's talk about this guy here. 2, 3, right? A2, 3. 2, yes, I am in the second equation. So this is R, raw, and this is C. Of course, I'm talking about the second equation. The second equation, yes, which is the second raw, and the third column, so 2, 3. So that's the story of these guys, 1, 1, etc., and these indices. So yeah, of course, if you have any questions, if you'd like me to repeat anything, please write it down in the comments. I will try to answer as fast as I can. All right, now we know how a general system looks like, right? And we know all these details. Of course, what is our goal after all, right? Our goal is to what? Is to solve the system, to find all the possible solutions. Now, in general, a system might have a solution or might not, or maybe more than one solution, right? But I mean, either a system does have solution or solutions or not. A system which has one or more solutions, right, is called a consistent system. So consistent means has one or more solutions. Inconsistent, of course, will be what? Will be the other case. Inconsistent, right? Inconsistent means that this system has no solution. Let me show you simple example on each of these. For the consistent, let me start with the consistent case. Let's go with this guy here. X plus or minus y is equal to 1, and x plus y is equal to 3. I'm starting, of course, with a very, very simple, system, just for you guys to understand with this terminology, and then move on to matrices. Of course, I believe that you all know how to solve this system. The solution will be x equals to 2 and y is equal to 1. So we got a solution. We got only one unique solution, but at least we did get a solution. So this is a consistent system, right? What if we have something like this? Let me just erase these. Let's assume we have something like this, or maybe let me just add one more letter. Let's say x minus y plus z is equal to 3. That's a linear system. Well, linear equation, but it's a linear system. I can call it a system which contains one equation. One equation and 3 unknowns, right? We have an infinite number of solutions. Let's consider, for example, let's give x the value 0 and the y value 0, then z will be 3. If I give the x the value 2 and y, let's say the value, let's go with maybe minus 3, right? So negative 3 cancels with this guy, so z is equal to negative 2. So each time you just pick values for x and y, or any of these two variables, you're going to get a solution, right? So this means we have an infinite number of solutions. So this is also consistent. Okay? In general, in the end, well, this represents a plane, right? All the points which are, have coordinates x, y, z, which are the solutions of this equation, if you put them all together, they're going to form the plane. Well, this is, we're going to, of course, talk about it in details when we talk about lines and planes. Anyhow, this is what it's meant by consistent systems. Let me give you an example about an inconsistent system. Let's go with something like x plus y is equal to 1, and x plus y is equal to 5. Now, wait a minute. How come x plus y is equal to 1 and 5 at the same time, right? It doesn't make sense. Well, again, if you subtract, let's say you subtract these two equations, you'll get x minus x, that is 0, y minus y, that is 0, equals to 1 minus 5, that's a negative 4. That's impossible. This is an inconsistent system. So this is meant by consistent and inconsistent systems. Beautiful. Now, let's come back to the general case of what? Of the linear system. We have a large linear system. I mean, really, it's a huge system, and it'll be nice if there is a way to write it in a more compact form. Okay? Because later on, we're going to use this compact form in order to solve the system in an easier way. I mean, well, this is a 2x2 system. Even if you have a system with 3 equations and 3 unknowns, right? That's doable manually. But let's say you have a system with n equations and m unknowns. I'm talking about hundreds, maybe thousands of variables. Literally thousands or maybe more. It's impossible to solve it manually. Even if you're going to use a software, right? we need to adjust the system in a way in order to reduce the complexity, to reduce the time of solving this system. All this, in order to do all that, we first of all need to start to write the system in a compact way. And this is where the matrices pop up. Now, let me show you what a matrix is. Let me just erase first. All right. A matrix, what is a matrix? A matrix is a rectangular array. Rectangular array of numbers. Something like maybe 3, 4, 2, and -1, 6, and 1. Something like that. Let me do another one here. So it could be 0, 5, 1, 3, 6, 2, 8, -1, I don't know, 10 over 7, anything, right? These are matrices. Now, these are, as I said, arrays, rectangular arrays of numbers, but in general, more generally, a matrix is a rectangular array of objects. These objects could be numbers, as you can see, real numbers, complex numbers. It could be functions or other things. But of course, for this course, Introduction to Linear Algebra, we're going to restrict ourselves to these guys, real numbers, okay? Cool. Now, as you can see, each matrix consists of rows and columns, right? So this is the first row, R1. This is the second row, R2. That is the third row, R3. Similarly, C1, C2, column 3. Again, here this is row 1. This is row 2, column 1, column 2, column 3, etc. Okay? So a bunch of columns and rows. And I think you might be starting to link the matrix, these numbers, with the linear system that I talked about, right? Because again, there we talked about rows and columns. So there should be, you see this linkage? Cool. Before that, let me just say one more thing about the rows and the columns. So let's say, for example, this matrix here, let me call it A, right? That is 3 by 3, 4, 2, right? -1, 6, and 1. Now, as I said, we have 2 rows and 3 columns. Now we say what? We say that this is a 2 by 3 matrix. What does this mean? It's a matrix which contains 2 rows and 3 columns. So this is how we represent it. So whenever you see, M by N matrix, it's like they're telling you, wait a minute, we have M rows and N columns. So this is how we represent a matrix. Cool. Now, if you remember the general system that I represented, that I showed you, A11 x1 plus A12 x2, etc., right? Equal to B1, whatever. Now, how can I represent this as a matrix? Now we can see. Let me show you. All right. So this is a linear system, and I would like to represent it by a matrix, right? So what I'm going to do is I'm going to take all the coefficients. So we have A11, right? I'm going to take all the coefficients. So the first row will contain the coefficients A11, then A12, then up to A1n. And then in the second row, I'm going to have A21, etc., up to to A2n, down to the last equation. I'm going to put a line like this, and then I'm going to list B1 down to Bn. Now, of course, I'm going to show you the matrix, but first of all, I wanted to explain how to transfer a linear system, or to move from a linear system to a matrix. So I'm going to remove all the x's. I'm not going to write them here, okay? And I will just restrict myself to the coefficients. And this is what I'm going to get. Let me show you. So our first row will be A11, A12, A1N, right? B1, A21. Look, first row, first column. First row, second column. Second row, first column, always RC. A22, A2N, B2, down to, the last equation was AM1, yeah. AM2, AMN, and of course all the coefficients, sorry, I go down to BN. Now this is how a linear system looks like. Of course, the first column represents all the coefficients of x1. The second represents all the coefficients of x2 and so on. Now this matrix, which contains all the coefficients and the right-hand side, which is B1, B2, is called an augmented matrix. So the augmented matrix is the matrix which contains, as I said, all the coefficients with the last column. Why do we call it augmented? Well, because we have added, or we have, appended the last column. So this is what I call augmented. Now, if I'm interested only in the coefficients, let's say I removed all these, just want to talk about the coefficients, right? Well, in this case, it's not augmented. We call it a coefficient matrix. So this guy here, right? This guy here is called what? The coefficient matrix. Okay? All right? So that's what a coefficient matrix is. And moreover, if I'm only interested in the matrix which talks about the right side, which is B1, B2, down to Bm, right? This matrix contains one column and m rows, right? In each row, we only have one element. This is why we have one column. A matrix which only contains only one column is called a column matrix. Column matrix. So again, we have the augmented matrix, which contains all the coefficients of the variables and the right side. The matrix which only contains the coefficient of the x's is called the coefficient matrix, and the right side coefficient, the right side numbers represent or form a column matrix. Okay, perfect. Let me show you one numerical example now. Let us consider this system. This is a linear system. 2x minus y plus z is equal to 3, x plus 8z is equal to 5, and 3y plus 2z is equal to 1. Let us write it as an augmented matrix, right? All right, how we do that? Well, as I said, I just copy the coefficients, right? So for the x, we have 2, we have 1, here we have nothing, okay, 0. For the y, we have minus y, that's a negative 1. Nothing for y here, so 0, 3, 1, 8, and 2. And the right side will be what? 3, 5, 1. This is what? This is the augmented matrix, right? Now, what about the coefficient matrix? No problem. Let's remove this column. This is our coefficient matrix. And of course, 3, 5, 1 will be our column matrix, which represents the right side. Okay? Beautiful, beautiful. So now I believe that we know what a linear system means, and what a matrix is, what does it mean, and how to represent a linear system using a matrix. Cool. But we're still talking about representations here, right? Cool. I mentioned that I understand that this is a more compact form, but wait a minute. I mean, how would this help us solve a system, especially when it is large. When it's large, how would this representation, would such representation help me solve the system? Well, I'm just doing, I'm just copy pasting the numbers, right? I mean, I did not do any change. The equations are still lengthy. Again, this is a 3x3 system, but you know what I mean? I'm talking about large systems. Of course, we do need to adjust the system, to change it into a simpler system, provided we cannot change the equations. What am I talking about? In order to explain or answer about what I'm talking about, we need to talk about one more concept, which will be the last concept for today's lecture. We need to understand the operations that we are allowed to do for any system, right? For any system, so that the outcome, the equations do not change. Okay, because again, I need to change this system into another simpler system so that the outcome, the solution for this system is not changed, right? Because I need to solve this system after all. How would I do that? Or what are the operations that I can apply in order to convert the system into an easier one without changing it? Well, we have 3 operations. And we call them 3 elementary raw operations. That's super important. So we're going to now talk about something called elementary raw operations. So whenever I want to solve a system, a linear system using matrices, I have to, or I should be applying some elementary raw operations. What are these? The first elementary raw operation is the following. I can swap any 2 raws. In other words, let me just remove this guy here. Let us say for some reason, I want to interchange this raw with this raw, the first with the third, or the first with the second, or any 2 raws. Would this change the equation system? No, right? I can simply interchange any 2 raws. Now, in terms of matrices, what happened here? The first matrix was 2, -1, 1, then 3, right? 1, 0, 8, and 5, and 0, 3, 2, and 1. Again, this means that I can simply interchange any 2 raws. For this example, I'm going to interchange raw 1 with R3, right? With raw 3. So how would I write that? I can simply say that this matrix has changed into, I'm going to write the new matrix, but of course, we need to explain what happened here. So I write this, R1, double arrow like that, R3. Whenever you see this double arrow, this means I have interchanged the raws. So 2 minus 1, 1, 3 becomes in the last raw, 2 minus 1, 1, 3. And the third becomes the first, so 0, 3, 2, 1, and the second remains as is. Okay? So the first elementary raw operation is to interchange any 2 raws. Now, why do we do that? This will be later. I will explain later how would this help us. But for now, let's just understand then what the elementary raw operations are and what we are allowed to do for a matrix. Second elementary raw operation is, let's say this is the first equation, and for some reason again, I would like to multiply the entire equation by a constant, let's say by 3. So this becomes what? This becomes 6x, right, minus 3y plus 3z is equal to 9. Did it change the equation? No. It just multiplied the left and the right side. Nothing changes regarding the solution. I'm still respecting the equation. So that's the second raw operation, which is to multiply any raw by any factor, by any number, of course, non-zero. So for example, let me just copy the main matrix here again. Now let's say I want to multiply the first raw by 3. Of course, you can multiply more than 1 raw at the same time, right? But now let's just multiply 1 raw. How would I write that? I would say, Okay, now here I want to change R1, right? R1, the first raw will be changed. So R1 becomes one arrow. R1 becomes, or R whatever it becomes, this means I'm going to change this raw. So I'm going to multiply R1 by 3. So R1 now becomes 3R1. So this becomes 6, 3, 9, and the other raws remain as is. And that's the second elementary raw operation. So swap, that's the first. Second, multiply any raw by a constant. Third raw operation. Now the third raw operation tells me that I can multiply any raw and add it to another raw. Okay, so if I multiply any raw by a number and I add it to another raw and then replace it with a new raw, it's not going to change. Let me give you an example. So for example, let's say I want to change R2 by the following. I can multiply R3 by a number, let's say 4. So 4R3. So multiply a raw by a number and then add it to another raw, R2. Okay? So this is the third elementary raw operation. And again, it's not going to change the system. I just multiplied any raw by a number, added it to another raw. So it's not going to change. And the new system becomes here, or the new matrix, I mean, becomes what? The first raw remains unchanged, as well as the third raw, 0, 3, 2, and 1. Now, what happens here? So R2 plus 4R3. Now this raw, I have to multiply it by 4 each term. So this becomes 0. This becomes 4 times 3, 12. 4 times 2, 8. 4 times 1, 4. Of course, I have to multiply everything. So this is what? This is 4R3, sorry, plus R2. Then what? Then I add it to R2. So multiply R3 by 4 and add it to R2, you see? So 0 plus 1 is 1. 12 plus 0 is 12. 8 plus 8, that is a 16. And 4 plus 5, that is a 9. So this and this are equivalent matrices, or equivalent systems, I mean. Right? Because we still haven't changed the solution, right? So in short, again, these are the three elementary raw operations. Swap any two raws, multiply any raw by any constant, and you can multiply a raw and add it to another raw. Now, how are we going to use these operations in order to write the system in a nicer way and to solve it in a faster way? That's what I'm going to show you in the next lecture. If you enjoy this video, I invite you to subscribe and like. And if you have any comments, any suggestions, please, I'm always happy to listen from you. And yeah, see you in the next time.